In this module, I'm going to introduce the pigeonhole principle. This module is fairly short. Uh, in terms of concepts, it's not that complicated, but I want to sort of show you with a couple examples that uh, why this pigeonhole principle is useful in a lot of problems. And we will do some of these problems in class. So here is the statement of the pigeonhole principle, which says if I have two sets S and T such that they are finite sets and the cardinality of S is greater than cardinality of T, in that case there is no one-to-one function from S to T. Essentially T has smaller number of elements, and that means that something has to give. Two elements in S have to be in mapping to the same element in T. There are lots of different ways this principle is described. You might have heard it described it as if you have n holes and you have n plus 1 pigeons, then at least one hole must have at least two pigeons. The proof is trivial, we are not going to get into it. So let's look at an example of where we could apply this, where it's not dealing with pigeons, it's dealing with something that we can see in other contexts. So what this is saying is, if I look at a decimal expansion of a rational number, which is not an integer, so we are not looking at 4 divided by 2 kind of thing, then after a while it's going to be periodic. That is, the same numbers are going to repeat again and again and again. So let's look at why this is the case. We'll look at this for two random numbers p divided by q. We will illustrate it with one specific example, but it's important to realize that whatever we are doing will work for any p and any q. So let's look at this example. Here I'm going to illustrate it with p equal to 29, q is equal to 54. But again, what I want to emphasize is the argument that I'm going to make is going to be independent of what these two specific numbers are. So let's look at how we obtain the decimal expansion of this number. Think about long division to get the decimal representation. So we have this number 29.00000000 forever. And our job is to figure out what the remainder would be at every step. So first of all, how do we do the division? Well, we start with 29. Well, we don't have any 54s that can go into 29, so we get another 0. In this case, 54 times 5 can go into this, so that will be 270. So the quotient will be 0.53, sorry, 0.5. Then we subtract, we get 200. Again, we see how many 54s fit in 200. That will be 162. So 54 times 4 is 162. The remainder will be 38, and so on. Now, even though I'm illustrating this with 29 and 54, whatever I have said will work for any numbers p and q that are integers. Now, a few things I want to focus on. I want to focus on the remainder that I'm going to get every time, and I'm also going to look at the quotient that I'm going to get at every time. So I have a question. Is the remainder guaranteed to repeat? My claim is that eventually the remainder will repeat. I will see the same remainder coming up again. Why is that? Pause here for a little bit to think yourself. So the reason the remainders is going to repeat is because remainders can only be between 0 to 53, or more generally from 0 to q minus 1 if we are dealing with random p and q. That means the remainder is bounded. However, the actual division will go on forever, and that means I'm basically creating, in this case, a function from numbers that are set of integers, or we could think of this as the set 1 through 55, for example, to 0 to 53. And because the set S in our case is bigger than set T, set S is uh, essentially the set of integers or some large number bigger than 54, and set T is the set of remainders which is from 0 to 53, and that means some remainder is going to repeat. Now let's look at what happens if the remainder repeats. So suppose the remainder that repeated happened to be 20. If the remainder that repeated was 20, then the rest of the long division that I'm doing will repeat exactly the same way. And that means that the quotient that I'm going to get will repeat as well in that situation. Now, some of you may be concerned that what if the numbers are like 2 divided by 5? In this case, what is repeating is a bunch of zeros, but that's okay. All that we are saying is it's going to repeat forever, but what it could be repeating is a bunch of zeros. Let's look at one more example. Let d1, d2 up to dn be positive integers. They're not necessarily distinct, but we have n of those numbers. Then the claim is sum of these numbers add up to a number that is a multiple of n. So let's look at an example. Let's say if I have the numbers 1, 1, 5, 5, 10, 20, 36. I have 7 of these numbers. Then my claim is that I can add sum of these numbers to get a sum that is multiple of 7. So let's see why this is true. What we're going to do is we're going to take the numbers that we have and we're going to add them one at a time. We are going to start with the number 0. Then the first number is b0, which is 0. I'm going to add the first number. That will get me d1. Then I'm going to add the second number. That will give me b2. Then I'm going to add the third number. That will give me b3, and so on and so forth. An observation here is that these are a total of n plus 1 numbers. Pause here for a second to make sure that you're okay with this. Alright, so now I'm going to take these numbers and each one of them I'm going to do modulo arithmetic to find the remainder. So I'm going to divide each one of these numbers and find the remainder. So in this case, I will write b0 as sum k0 times n plus r0. Now in this case we know b0 is 0, so that means k0 and r0 are going to be 0. But let's not worry about that for the time being. I will get something about b1. I'm going to write it as k1 times n plus r1. b2 I'm going to write as k2 times n plus r2, and so on and so forth. Next, what I'm going to do is I'm going to only focus on these remainders. Once again, where do these remainders come from? Well, the remainders have to be from 0 to n minus 1, because I'm dividing by n. That means the remainder has to be less than n and it can't be negative. However, there are a total of n plus 1 numbers in here because I started with n plus 1 numbers here. I got a remainder of each one of them by dividing with n, and that means the total number of things that I have here is n plus 1, but the total choices that I have is only n. That means some number somewhere has to repeat. So let's say that the repetition is somewhere. Without loss of generality, let's assume that the repetition is for bj and bi, and we will also assume that j is greater than I. Basically let I be the smaller number, j be the bigger number. So that means if I look at bi minus bj, then that is a multiple of n, because the remainder is the same. So if I write bi minus bj, it's going to be some kj minus ki times n. But what is bj minus bi? It's basically the numbers that were added in between, which is d of I plus 1 plus d of I plus 2 plus d of I plus 3 all the way up to d of j. And that is a multiple of n, and that's exactly what we wanted to prove. I want to emphasize here, make sure you solve problems on this from the textbook. Pigeonhole principle is very simple, uh, but it is also useful in a lot of instances. So being familiar with pigeonhole principle will be something that would come in handy for a lot of different situations. Uh, but it's sort of hard to see how pigeonhole principle fits in the given problem, and solving different problems will help you gain that understanding.